there are other types of sequences. The other type of sequence that we will be concerned with in IB is the geometric sequence. So for the arithmetic sequence, we said, hey, look, we have a bunch of terms and they have a constant difference between them. Well, that's through the operation of addition or perhaps subtraction. Your constant difference d doesn't have to be a positive number. D could be equal to -3, for instance. Could be. And then u1 could be equal to, I don't know, 20. These could be anything. As long as it's an arithmetic sequence, these two could be anything. Okay, but let's talk about the geometric sequence. So a sequence is called geometric when each term is multiplied by the same value to get the next term. Now, if we look at the pattern between the term number and the exponent of r, we can see that the formula for any term in the sequence is actually given by un equals to u1 times r to the power of n minus 1. Now, again, this is a new formula, and it might be like, oh, okay, another thing I have to memorize. But don't memorize it, okay? You can try to memorize it if you want, but it's much more useful for you to actually just look at this equation for a little bit. Just, take a look at every term and think about logically, what is this expression actually doing? What is it telling me? Well, for the arithmetic sequence, we said that there's a common difference, right? So you add something every time. For the geometric sequence, instead of adding something every time, you just multiply by the same number or by the same value to get the next term. So let's say, for instance, you start with a sequence. I'll give you an example of a geometric sequence. It looks like 1, 2, 4, 8, 16, etc. Now, if you look closely, this isn't an arithmetic sequence because, well, here there's +1, but here there's +2, and then here there's +4, and then this is +8. So since we don't have a constant common difference, right? Or rather, we don't have a common difference, it's not an arithmetic sequence. So I'm going to have to look at what else could it be. Now, fortunately, we only have to worry about arithmetic and geometric sequence, so if you just take a quick look, you would see that from 1 to 2, this is a multiplication by a factor of 2. From 2 to 4, that's a multiplication by a factor of 2. And then from 4 to 8, multiplied by 2. From 8 to 16, multiplied by 2. And this is a common ratio. That's where the geometric sequence comes in, right? And so we can see that the r value for this sequence, so again, u1 would be equal to the value of the first term in the sequence. And then the value of r is just the common ratio. So r is the common ratio. And in this case, my common ratio would be 2. So let's write it out. So for this sequence, I would say the general formula or the general expression for this geometric sequence is un equals to 1, which is my u1, times r, which in this case is 2, to the power of n minus 1. Now let's discuss again the n minus 1 for a moment, so that you don't get needlessly confused. The only reason we add an n minus 1 here to the power of n minus 1, right, is first of all, you see how it's multiplied by 2 every time? So for sure, you're going to have something like times 2, times 2, times 2. And then depending on the number of times that you multiply by 2, you're going to have 2 to the n. You're really going to be multiplying whatever initial value you started with times 2 to the n. However, because we want because when n equals to 1, we want u1 to equal u1, which is redundant, I know. Looking at this formula, let's say if we replaced my 1 with u1, it would have to be true that u1 equals to u1 times whatever this is. This here has to equal to 1. So in this case, it's u1 times 2 to the 1 minus 1, that's really just u1 times 2 to the 0. And then what is 2 to the 0? Anything to the power of 0, with very few exceptions perhaps, is equal to 1. And so we would have u1 times 1. So really the only reason that the geometric sequence has this n minus 1 in the exponent is just to remind you that, look, when n equals to 1, u1 equals to u1. So this part of the expression must be equal to 1 so that it doesn't change the value, so it's consistent. And the only way to really get that is to say, well, look, you're not going to multiply by 2 for the first term. You're only going to start multiplying by 2 for every term after the first term, which would be expressed as n minus 1, or r to the n minus 1. Okay, so let's take a step back for one moment, and let's take a look at the example. Okay, so the example was 1, 2, 4, 8, 16. So I would write it as un equals to 1 times 2 to the n minus 1, which we can just simplify to 2 to the n minus 1. And so un is equal to 2 to the n minus 1. And then now I can find any single term in the sequence of the geometric sequence un. So u1, when n equals to 1, u1 equals to 2 to the power of 0, which equals to 1. When n equals to 2, u2 equals to 2 to the power of 2 minus 1, which equals to 2. When n equals to, when n equals to 3, u3 is equal to 2 to the power of 3 minus 1, which equals to 2 squared, which equals to 4. And then finally, let's say n equals to 4, u4 equals to 2 to the power of 4 minus 1, which equals to 2 cubed, which equals to 8, and then et cetera, et cetera, et cetera. And as you can see, we have every single one of the terms, every single term in the sequence, without having to write it out like this, right? This is really the beauty of it. You have an equation, you have an expression, you just tell me which number in the sequence you want, and then using the formula or using the equation, I can tell you exactly what that value is. So for instance, if I asked you, well, what is the 29th term of the sequence, right? What are you going to do, write them all out? No, you're just going to use the formula. You're going to say, well, for u29, n is equal to 29, right? And so if I look at my formula, this is my un equals to 2 to the power of n minus 1. I could say u29 is equal to 2 to the power of 29 minus 1, which equals to 2 to the power of 28. Whatever number that actually is. I'm not going to calculate. That's a pretty big number. Okay. And that's pretty much it for geometric sequences and arithmetic sequences. Next time, we're going to explain arithmetic series and geometric series, and then we'll do some problems. Thank you. Math can be difficult, but it doesn't have to be. Let's clear things up together. You can use the link in the description below to schedule a session with us. Make sure to like, comment, and subscribe to get notified when we release new content. Thanks for watching, and I'll see you next time.